Hey all, and welcome to the first Lambda Lounge of 2021. Hope you all had a good New Year as much as possible. This month, we're lucky to have Michael Arnaldi from Matex, who's the creator of the EffectTS library, which is a library you can use to do lots of cool stuff in functional TypeScript. So without further ado, let me bring him on board. Hey Michael, how are you?
Hi, very good. You?
Yes, good, thanks. So let me just get rid of my presentation and add yours. So 1 second. There we go. So I'll let you carry on for now. So I'll vanish unless there's any questions and stuff that people want to raise. So if you do have any questions, put them on the YouTube stream. I'll highlight them and maybe pop in to just say them as well. So yeah.
Perfect. Am I on screen?
Yeah, you are on screen.
Good. So first of all, thanks for having me. It's really a pleasure to be here. And I have to say I'm very excited about the opportunity to speak publicly about EffectTS, which is a library we've been working on for about a year and a half. And it's definitely something I'm proud of. And I hope it's going to be a really nice presentation for everybody. So a few intros before anything. A few words on Matex. We are a tech hub. We develop primarily in the open source space. We do tons of R&D, and we offer workshops, team building, outsourcing, design, and equity partnerships for, well, basically any kind of company. This presentation will really have very small amount of slides, and we'll jump to code as quickly as possible, as I believe it's the only, the code speaks for itself, much more than words. So first of all, let's start. What do we mean by functional programming? Many have strong opinion. I really don't. I think functional programming is about programming in a declarative manner, and it aims to simplify, or at least it should aim to simplify, day-to-day operations that every one of us went through many times. How do we do that? Depends by the language and by the context. There's not a single solution, and well, the silver bullet doesn't exist. Many have tried and failed to implement Haskell, where really functional programming is born in the classical sense of typed functional programming in other languages. I don't think we should do that. I don't think we should do that because it doesn't fit well in different languages, and forcing the same methodologies, forcing the same patterns can lead to very complex code and very hard to understand how to write it properly. And I'm not against Haskell for in any way. I actually love the language. It's just in that syntax, in the Hindley-Milner type system, it does make a lot of sense. Outside that that area, it tends to be overly complicated, especially in languages without native support for higher kinded types and for implicit type classes. So what's happening in functional programming lately? Just about 2 or 3 years ago, there has been a lot of R&D in Scala, trying to get functional programming at a level that is productive, really, for business, and it doesn't present the same mental challenges of traditional functional programming. And another important part is the performance trade-offs. Namely, Zio was born. What do I mean by performance trade-off? The abstractions, every time we make an abstraction, there's a price to be paid for the abstraction. And in Scala, for example, given the compiler itself doesn't do strong forms of optimizations, and I have to say, sometimes not even in Haskell, things works just fine. We tend to add a lot of overhead, and we pay the price for the abstractions. When Zio was born, and namely when when John added the environment parameter to 0, it was really a key moment. Personally, from totally disliking the functional programming patterns in Scala, I began to actually like it. So I had to try something in production. I've refactored a few services and really realized it was a big leap forward. And what do I mean that? Sometimes we say functional programming is testable, functional programming is good, but if you do functional programming with tagless final approaches and overly complicated things, it's hard. And if you don't do so, you lose testability. So functional programming, as in composing pure functions, you don't need any type class to do that. You don't need any strange stuff to do that. The problem is it's not testable. Because function composition, you can't decompose functions and test each pieces independently, especially if they are very, very well packed. You can still test the single components, but how are you gonna mock one into the other? There's really no easy way. And the classical solution is to use tagless final, which basically brings everything to an abstract level, and then you can swap in things for testing. You can say this service is replaced without using mocks or strange tricks. Problem is, it's not easy, and not easy to write, not easy to read, and not easy on the compiler. With Zio, we get the same level of testability, as in the same level that tagless final provides, in a much simpler way, in a way that doesn't require a lot of mental overhead. Like, for example, it doesn't require speaking about monads, applicatives, functors, and all the jargon that you might know if you are a functional programmer. I promise this is gonna be the only slide where I actually mention monads. So we are gonna do functional programming, we're gonna do statically typed functional programming, and we're not gonna speak about jargon. We're gonna go straight to the point. From Scala to TypeScript. First of all, why? Why in the hell we decided to build something out of TypeScript? In Scala, I was happy, as I said before, but we definitely used a lot of TypeScript. I knew the language very well, but I didn't like at all how we were using it. I knew that TypeScript was very powerful, and the static type system is insanely flexible. And here I really mean insanely flexible. There are some kind of types in TypeScript that you won't see in any other language. And the reason is they are trying to type over, they are trying to add types over what usually is a dynamically typed environment that is JavaScript. So the level of weirdness they had to add at the type system level is insane. It's not really Scala, and one might argue, you said in the slide before that you don't think it's a good idea to just port one language into the other. And I have precisely the same opinion about porting Scala and TypeScript. It's not a one-to-one port, but the features of the language are very similar. Both are languages where you see the both aspects of object orientation and actually functional part. So the kind of principles you can apply are very similar. From a syntactic perspective, we did a lot of changes, but at the API level, we got something that is extremely similar, and it can really be used in a smart way. So the POC time started, and at the beginning, it was really, I didn't even know if it was possible or not at some level. And here we begin with FFTS. The POC actually worked out really well. Took just about 3 months to actually write and to figure it out type-wise how things could work. The POC wasn't really a port of Zio. It was a port of the ideas of Zio. So we didn't care about performance. We didn't care about safety. We didn't care about anything at all. We cared purely on if we could encode a similar type of API, and if everything worked out, would have worked out. It did work out, and I was finally able to, after a few months, to properly design all the required pieces. Namely, one of the hardest part was variance. Scala has explicit variance annotations. So when you define something, you can say, okay, this parameter is contravariant, this parameter is covariant, this parameter is invariant. And that's how you say how the parameter should behave. In TypeScript, this is implicit, and it's derived from the structure of the data types you are encoding. TypeScript has a structural type system, so everything is structural, including variance. The only problem is not being explicit. You have to pay a lot of attention, because as soon as you touch something in a wrong manner, the implicit variance of the parameters completely change, and well, the variance breaks. This was a huge problem at the beginning. We've tried to implement a fluent API, so like you would do in Zio, where you concatenate stuff by saying this dot that dot that, and etc. etc. That doesn't work in TypeScript, so we had to go on a different direction. FPTS in TypeScript already had a pipeable API that sort of worked around the problem by separating the data side of a data type and extracts all the behavior functions. So they are no longer inside the same data type, and by definition, then they cannot affect the variance of the type. So I tried that type of API. I have to say it worked really, really well. So after the POC, it was time to take the project seriously, and I began a full port of Zio. What do I mean by a full port of Zio? Full port of Zio means starting from the very same primitives and the very same fiber design, almost to the line by line. If you look at the code base of Zio and you look at the code base of FFTS, apart from the modular structure that obviously is different, and apart from the style of the API that is different, because Zio is a fluent API, while FFTS is a pipeable API, line by line, they mean the same thing. That means we could support the same level of complexity, and we could support the same refinements and multiple data types that are built on top of the very basic. And I do believe this API is really nice, and I think it will become some sort of standard because it works really well in Scala. It works really well in TypeScript. I've begun to see other people trying to do the same in C#, and there's something working on someone working on a port to Swift. So this is very interesting. Why I say it's very interesting? Because everything has a learning curve. And I'm not gonna lie, FFTS has a learning curve, and it's not the easiest thing you could learn. But once you learn FFTS, or once you learn Zio, you are able to directly use one or the other with a very quick ramp up. I have had the experience of people coming from Zio having to implement something in Node.js. Well, in less than a week time, they were pretty much ready to go and completely comfortable in in the API. And the same works the opposite way. I've trained some people in Effect.js, and they were perfectly able to use Zio in Scala, having learned, of course, the differences of being in a Node.js environment or being in a JVM environment. The two things are quite different as of runtime, but syntactically and logically, you can apply the same principles. And even Haskell is, I see a trend where in the last few years, there's many effect libraries that have come out. One that we really should mention is Polysemi, which sort of turned the point to an API that is really nice. It's not that fast. At the beginning, we thought it was almost cost-free. Turns out it's not, but that's really not the point. There is active work, even in Haskell, to build highly performant effect systems. Namely, Alexis King is building F, which will be basically a cost-free effect system. And the idea is very similar. At the low level, also the effect system of Haskells are implemented in a very similar way. Clearly, with the differences of the language and everything else. But once again, it's about principles. You can apply the same principles regardless of the context, which I believe is a very powerful thing. So what's inside the box? A lot of things. And when I say a lot of things, it's really a lot of things. That's just 5. And I don't think any presentation, any number of slides would have covered the whole thing. I believe the numbers of functions and combinators in the system is actually on the tens of thousands of combinators across various data types. So the thing is really big. I don't think an application exists that needs everything that is inside the box. But for sure, any application will benefit from some parts of some data types that are in the box. Starting with very important things, we have fibers. So you can think of a fiber like a very lightweight thread. Clearly, in Node.js, there are no threads, so it seems counterintuitive, but there's still concurrency. Fibers are lightweight threads that can be allocated in each of the threads. And Zio does a very good job of using thread pools and et cetera, on the Scala side. Clearly, in Node.js, we don't have threads, so that part is actually slightly easier. It's implemented precisely in the same way, but it is slightly easier. We have effects, which are both pure and impure computations, modular, reusable computations. We have managed resources, like things like a database connection, where you have an open stage, you then use the resource, and then it has to be safely closed. There's a lot of semantics in a managed resource, because, for example, the closing step has to run anyway. It has to run if the computation succeeded or if the computation failed. As long as you've opened the resource, you've got to close it. And that's done automatically. And you can compose managed resources. You can have a database. You can have a cache. You can have many things. And all the logic of opening this stuff, using and closing once you are done, or interrupted for any reason, the resources will be closed. Layers. What are layers? Every application has a dependency tree. If you ever wrote a real program, you're gonna have dependencies. And it's fine, you can pass the dependencies as arguments and everything else, but even if you pass them as arguments, you gotta have to construct the dependencies. constructing dependencies is not easy. It's one of the most complicated parts in a software. You don't really want to use dependency injection frameworks that just sort of hide where dependencies are initialized, how dependencies are plugged into your application. You do want to have clear and declarative stuff. As we said before in one of the first slides, functional programming is about programming in a declarative way, telling the computer, your system, what it should do, not how. The how is an implementation detail. Layers optimize the dependency tree construction. They are built on top of managed resources. So a layer can be a connection pool, a layer can be whatever you like. And you can compose together layers. You can say these two dependencies shall be constructed in parallel, or these two dependencies, well, this dependency depends on another dependency. So first you have to construct this, then you have to construct that. And it's all, again, very, very declarative. And it's sort of at the edge of your system. So you extract all of this from your business logic. Then you have many more data types and primitives in the box. Just to name a few, there's queues, semaphores, streams, very powerful data type. I don't know if we're going to have enough time to even look at streams, but it's really, really a nice data type. Pretty much all the data types in the box have the same shape. They all have an environment. They can all fail with errors. And they pretty much all have the famous 3 parameters that Zio has. So what this talk was called is called practical functional programming in TypeScript with effect, yes. What do we mean by practical? Practical is functional programming without any jargon. Functional programming focused on application level stuff. As we saw in this previous slide, each of the blocks that you will find has a business use case and has a real business use case. You won't find things like catamorphisms or recursion schemes, which are fascinating, to be honest. I like them very much. But you are rarely applying a recursion scheme on an application that you develop on a day-by-day basis. But you're going to have dependencies on application that you develop on a day-by-day basis. You're going to have managed resources if you're doing anything interesting. As soon as you connect with something, it's a resource that should be managed. So how does development look like in this environment? Well, one sentence I really, really like, and I think either John or one of the Zio contributors came out with this definition. I don't really remember who, so forgive me if I'm not doing proper credits. It's Lego-like development. Take the blocks and compose. Like Legos, you start with these small blocks, plug them together and build castles and beautiful stuff. I even saw a Ferrari, the outside of a Ferrari built using Legos. That's the same thing. You take the blocks, compose it, and a beautiful thing will come out, and it will stay everything together because the blocks are properly designed and attached together. Laws. Functional programming in the classical sense is all about laws. Practical functional programming is not that much about laws. In fact, I believe most of the data types we have are law-breaking in some senses. It doesn't mean they're useless. It means sometimes focusing on the laws and on the mathematical side of things. I have a background in mathematics, so by all means, don't think I'm judging in any negative way the mathematical aspect. But we have to adapt the mathematical aspect. So we prefer usability over those. Effect is a data type that has fibers in it. Every time you spawn a fiber, you're doing parallel stuff. When you're in a parallel world, laws don't quite apply. In cats, for example, in Scala, you have the parallel type class, which tries to put some laws around the fact that you are in a parallel infrastructure. We don't care. We don't care about the types being lawful as long as they do respect the laws in standard conditions, and as long as the law breaking is useful for business purposes. And another thing, we don't focus too much on type classes. We do have type classes. Not it's an advice to use them at the API level, but they are even nice, to be honest. In TypeScript 4.1, given the variadic tuples that they've added into the language, we are actually able to simulate a higher kinded type. Not a generic higher kinded types with potentially infinite generic parameters. We have to fix the number of possible parameters to use, but apart from that, they do look like real higher kinded types, and so we could do real type classes. They're not going to be implicit, so whenever you use a type class, it's going to be a manual plugin. But as I said, we are not going to look through type classes today. If you want to have a look in the library, there are a lot of type classes too. They are very useful for the common behaviors that you know from type classes. But on a general application, I think they're probably going to be useful for 2, 3, 4% of the actual code. So most of the things are not don't require any understanding of type classes. And the type classes that you are going to use and that you're going to find useful are the very simple one, like equal. Type class equal means define the concept of equality for a specific type. Or type classes like a monoid, where you're specifying how things combine. So you have like a list. It can be concatenated. That's a monoid. Those patterns are very common. We don't call them in the classical sense. We don't have a monoid, for example. It's called an identity in the jargon of practical functional programming, and it comes from the work on Zio Prelude. Zio Prelude is the Zio take on type classes and hierarchies. So there is a very good presentation from John DeGo from about 6 months ago when Zio Prelude was published, and it has some nice properties. Like one that really shines is the fact that they define the applicative in a completely different way. But we said we're not going to talk too much about type classes, so let's not get into that part of details. It's time to code. Sorry that I've bothered you with 8 slides, and thank you for your patience, but an introduction was slightly necessary. So let's get to the interesting part and let's see some code. So, VS Code. If you touch TypeScript, I really advise on VS Code. It's pretty much the best editor you can find for TypeScript. I'm not saying general stuff, but for TypeScript, it really works well. And it's kind of important because we are using pretty much always the latest version of TypeScript. So that sometimes is not properly supported in other text editors. So we said at the beginning, there are some API choices that we've we've made. One of which is the pipeable API versus the Fluent. We are not using Fluent APIs, we're using pipeables. Just take a minute to show you what it means. First of all, a Fluent API is something like the thing you will find in a promise. So you have like you concatenate things calling the dot. Then, and etc. etc. And that starts in this way. Problems with this approach, it's not extendable. All the combinators have to be within the data type. And in TypeScript, it doesn't really work for variants. How are Fluent APIs encoded? Fluent APIs are encoded through sort of class where you have generic parameters. And then you have methods that use the parameters. Here, for example, if this is my data type, all of those parameters are actually bivariant. There's really no variance implied. The moment I do something like that, I'm specifying a function that returns an R. In this case, R will be covariant for TypeScript. If I do that, it's going to be contravariant. We have to say that in Scala, here you would use a plus, here you would use a minus, and etc. etc. And in Scala, if you specify the variance and you try to add some behavior that breaks the variance, then you get a compiler error and it doesn't work. In Scala, Zio has variance definition applied, and in Zio they are able to do so mainly because of implicit evidences and the implicit system that Scala has. TypeScript doesn't have this, so we are not gonna use any Fluent API. Our APIs are gonna be based on the pipe function. The pipe function is defined as a nightmare of overloads in TypeScript, but basically it says, given, for example, a number, which is a data type, you can compose functions and so on. And you can do multiple steps, and etc. etc. One clear advantage of this is the data part. This is behavior functions. They are completely separated. So you can add new functions. You can extend the behavior of the data types without ever touching the internal part of the data type. That is very important also for other reasons that have nothing to do with variants or with complicated topics. In TypeScript, you do want to build things that are shakeable. When you compile it to get to a browser, now we do target both Node.js and browser. Today, we're going to see primarily Node.js stuff, but you can totally use it in the browser, and we even have dedicated data types that are very lightweight, completely for the browser. You want things to be shakeable, so that you have tools like Webpack that can understand which portions of the code are not used and trash them out. As I said before, in the whole effect system, we have roundabout, well, I'm not going to estimate a number, but it's on the tens of thousands of data types, of combinators over the various data types. if you think that they could be all bundled in the same JavaScript file and shipped to a browser, you're gonna end up with a bundle of like 5 megabytes or more, which is the situation that you get if you use, for example, Scala.js, because Fluent APIs are non-shakeable. So that's the sort of APIs we're gonna look into. But let's get into the details of effect. We're gonna start with every new library, I believe, or any new language has to start with the same example. Hello world. Here, what do we say? Hello world is an effect total. It means it's not a pure thing, but cannot fail, and it doesn't need anything else to be used. An effect total, as you can see here, is just the effect library. Everything is exposed in effect.js/core. Here you have slash many things. Everything that is effect related, you're gonna find it inside effect. So all these modules that you see here are all built on top of effect. And as we said before, you have fibers, layers, managed, promises, queues, references, monadic references, schedule, which is a clock-like thing. And you can say, for example, I want to repeat these over a dynamic schedule and go in many complicated patterns. We have supervisors. As we said before, we have fibers. One process can spawn up different fibers. You have automatic supervision of those fibers. So if the parent dies, the childs are interrupted. If you don't want to interrupt the childs when the parent ends, there are ways to override the fork scope, it's called. And then they're going to be supervised by the global supervisor rather than the local one. I would have to say that in Zio, you already have decent documentation. In effect, yes, currently we are not yet 1.0, so the documentation is not already available in a website form, but all the functions have a documentation. And if you use namespace imports, this is called a namespace import, they are easily discoverable, and you can basically read the documentation of everything easily from the editor. The plan is then to build something that extracts those comments and place them into a proper website. Unfortunately, we were not lucky in auto-generating the documentation just yet. So I believe we have to build a library to generate the documentation in a proper way, which will take a while. But anyway, the same documentation of Zio can be easily applied to this library too. As I said before, there are hundreds and hundreds and hundreds of combinators. This is only effect. All of those combinators are only for one data type. I have another data type like managed that we're going to take a look at later. Same story. The combinators are going to be called very similarly. They're going to do very similar things, but this time they're on resources rather than on plain effects. Let's take a look at first of all, we are in TypeScript, so everything is well typed. We haven't wrote a single type yet. Why? Because the inference in TypeScript is fantastic. This program is inferred as a UIO, which means unfailable IO, and it's a short It's an alias for full effect data type, and this will be, the effect data type has 3 parameters. The environment that the computation requires. We said this requires no environment, so it can be called with any sort of environment, which is in TypeScript unknown. In Scala, it would be called any. And in TypeScript, actually, is a different type. This is sort of a weird thing for TypeScript. It can never fail. So the type of failure is never. And in this case, it doesn't return anything in particular. So it's just a void. This is the full data type of effect. So what we are going to see many times is types of this shape: effect, environment, error channel, result. This means an input, computation that requires something, computations that can fail for type errors, and in case it succeeds, they are going to get EA out. I don't like for the types to be explicit at all, because the inference is extremely good. So I'm going to erase the type. We're not going to see too much type level stuff. How do you run it? Well, you just called run main on the effect. Run main, what does it take? It takes an effect which has the default environment. In the default environment, you have things like clock, things like random. There are a few common effects that are used throughout the library. It can take any, well, it takes a generic error and really avoid computation, because your main shouldn't return anything. Now, TypeScript is flexible, so when you have a void, you can call it with something that returns something else. But the idea of a main function is the main function should run. It's not going to be about returning things. This is going to run, of course, asynchronously. And let's run it at least. Not going to be very fun with this particular example, but it will get interesting in a moment. So this runs, prints hello world, takes 3 seconds because I'm actually running the bare bone TypeScript file. So the first thing is Node has to compile everything. Clearly, you do want to run compiled code. You do not want to run, well, some people actually do run directly the TypeScript files because this is only bootstrapping. So it's not gonna compromise anything else. But I do advise to do proper compilation. We're gonna use a runtime that is specific to Node. You can run an effect to a promise. You can run an effect to a promise getting the full exit. But in Node, the run main has specific behavior. For example, it listens to the process signals. So whenever you have a sig term, it will automatically interrupt the execution of your program. That will trigger closing of all the allocated resources, and etc., etc. One other beautiful thing that the Node runtime does, well, actually, you can do this even in a browser, but the Node runtime sort of does it in an automatic way. It allows for easy tracing of the application, which is a topic we will get onto shortly. The first thing that starts is, how do we test this? How do we test this? We test it in a very bad way. We are still not using environments and similar stuff. So how do we test it? With basically a mock function. And those are the same kind of tests that you would write without an effect system. So that's not the way that we do want to test stuff. Let's get onto the second example, where we are beginning to see something different. So what's the problem here? We are using the console directly as a direct reference in our program. This means we haven't really clarified our dependency tree. This program to run actually requires a console, which was implicit by the fact that this is a module, but it's not extracted into a data type yet, into an effect type yet. So let's do that. So what do we want? We want the ability to run, to print something on a console. How do we define this? Simple interface. We can define a utility function that accesses the console service from within the environment and uses the console service from within the environment in the actual code. If you see the type of this function, it returns an effect that will need the console service to run, can never fail, and in case of success, returns void, which is the same result as before. We need to, well, first of all, let's use this. Even without specifying any implementation, I can use that, and I can see that this effectively requires my console service. Without providing the console service, I can try to run this, and I'm gonna have compiler error, which tells me you have to provide the console service, because the default environment that is clock plus random doesn't contain anything named console. Which means forgetting dependencies is impossible. And write a function that provides the console service. So it tells explicitly what the console service is about. And you can see that this function, what does it do? It takes an effect that requires the console service and anything else, has an error channel, an output channel, and the return type no longer has console service in it. So in this way, when we get to the main part, we can easily pipe the program to a provider, and this time we can run it. And it's gonna be exactly the same result as before. How does it look in tests? Well, we can make a test console to effectively test our program. Because whenever we want to test our programs, we don't want to test that the actual console prints something. You usually want to test something against the layer that sits right next to it. You don't really want to test everything every time. So we build a test console provider, which in this case just take an array of messages and just push the message into the array. We test the integration first. So we make sure that our live stuff, our true console, in this case, it could be a database or whatever else, works. So we test that the live service works. But in order to test the program, we don't need to wrap any live stuff. We can use a test provider, and we can assert qualities.
Just a quick question from one of the viewers that would like to know, how do you handle SIGTERM on Windows, if you know?
How do you handle?
SIGTERM signals on Windows?
It listens to both sig terms and sig int. So it should, at least it does work on Windows for what I've tested. I have to say I've never deployed a production system on Windows, so I don't quite know. But if you run the computation locally, the sig term, if you hit Ctrl+C, it does stop.
So maybe try it all and see what happens.
I don't have any interruptible program here. This just prints out in real time. But this has nothing special. This can even be extended. I mean, run, cancel. The canceller is a function, so you can totally control any sort of signal you want, anything. For example, the default is this. This is an effect. It has to run. So the default of run main is actually the couple of these two, but you can customize it however you want, depending on your system. I think it should work fine in Windows also, but it's definitely something I will test out. Even I'm thinking, yeah, in Windows works, but I am actually using a subsystem Linux, so that's sort of not the point. But I'll check it out, and in case it doesn't work, I will update it to make it work natively on Windows too. So that's how we test things. There's a little bit of boilerplate. We don't really like to define types manually. Well, some of us actually do like to specify types manually. I'm not of that school of thought. So let's get into step by step. We're gonna get through layers, and ideally, well, not much time, but at the end, you're gonna have a full database connection, and the last test is actually spinning up a Postgres, testing the database and closing down the Postgres automatically in a Docker container through an integration in test containers. But anyway, we can construct our console service as it was before. So it's just a put string line. In logic, same usage. Sorry, it's this one. So you have a make effect. We can derive the return type. So the A type, remember there was 3 parameters, one called R, one called E, one called A. In this case, we are saying the console service is the A type of whatever this effect returns. So if I add functions here, this console type, console service will have the functions. The second point is, in the previous example, we've had a console here. This is required because if we have multiple services, we don't want to have any conflict between the services. This is like an identifier, a unique identifier to target that specific service. This in Scala is implicit, in TypeScript is explicit, and we do it through a tag, which is a data type that you use in this way. So instead of saying access and specify the type, say access service, you push into the tag, and here you directly have the console service. Providing also becomes slightly easier, not too much. But this is the same type of signature that we had before. The type here is slightly different. It's called has console service, because this interface is purely, as we can see from here, the content of this interface is not even indexed. So we need some sort of discriminator, and that is represented by the has type. The has type is a completely fake type. Behind the scenes, when you generate a tag, there's a unique symbol that the tag contains. And what the tag is actually about, it has a constructor, so it can convert one console service to a has console service, or it can read from anything that has the console service and gives you the console service. It is low level. You don't need pretty much anywhere to use the type manually. You can just plug it into the combinators and use it directly. So this is the first step of abstraction. We're gonna now combine a few things. This program up now is fairly stupid, does only a single thing. I've never seen a program that actually does only a single thing in my life. So we should definitely start to compose some other things. Same as before, I'll skip the details. How do we compose things? We have functions like chain, which says runs this effect. That in this case, it's a pure value A. We chain it into a function. This is a point-free notation for this. So we can do sequential stuff. And we have, as we saw before, many other combinations, like this is doing sequential stuff, but not caring about the input of the previous. You can add, you have things like tap. All of those are called in precisely the same way as you will find in Zio. Tap, for example, it takes an effect, function, it returns an effect, and the result is discarded. So it doesn't change the result. This is very helpful for debugging or stuff like similar to debugging, or whenever you need to do something without changing the result. As we see, we compose in this way through the pipe function, and we can construct programs progressively. That's not the only way. First of all, we can see that there is a little bit of boilerplate in defining those helpers. It's the same in Zio. You have this sort of overhead. In case the functions don't take any generic parameter, we can derive those helpers automatically. So this is first part of shrinking stuff. Let's construct other services. Simple math service doesn't do anything interesting, but I have a number of functions, and here I say derive. I pass in the tag, and I automatically have my utility functions that automatically provides access and et cetera, et cetera. So this is a bit faster. The second and third arrays, the first one is for functions, the second one is for constants, constant effects, and the third one is for constants, like if you here want to access the tag. It's gonna be absolutely irrelevant, but you can derive accessor for those stuff too. So not only functions, constant or constant effects. Provider, same as before. Console service is precisely the same as before. But we're now going to see a different type of composition. This is a simulation of Scala 4 or Haskell Do, where basically at each step you keep progressing. Well, each step has access to the full scope of the previous. So as you say, you bind add 1 plus 2 to the variable a. B is done taking the variable a and dividing it. And at the end, we want to take b. Here we still have access to a if we want. And we print out a result. The type of this automatically requires both a math service and a console service. I remove this line. It's going to require purely the math service, and it's going to return, in this case, the full scope, which is A and B. As you can see, the number of types you have to write tends to get very small, and you get down to the actual logic. Let's do another step. We've seen only things that can only succeed. Let's introduce one error. For example, we are trying to divide by 0. I will publish all this code in the Discord channel, so you can all get access to it. It's already in a repo, so you will be able to take a look closely at everything. In this case, we say on the division, if y is 0, you're going to fail with a division by 0 error. And you can see that the types of these then returns an effect that doesn't require anything, can fail for division by 0, or can return a number in case of success. When we use it, we are going to see the division by 0 appearing at the type level. So we know that this can fail for this reason. How do we handle failure? Well, we catch the failures. And in this case, we said if there is an error, printout cannot divide this specific number by 0. Everything is inferred correctly. Whenever you catch an error, it's stripped. And this notation of using a tag here, personally, it's very important, because usually things will be failing for reason A or B or C or D. And here you want to catch and handle probably a subset of the errors. So using a tag, TypeScript is able to automatically narrow the types correctly. I have to say there is another error channel that's embedded, and it's a channel for defects. So even if you see something that can never fail, that's false. It never fails for a known reason. It might fail for whatever else. If you have a defect in code, an exception thrown, exceptions are never lost. There's a full cause that can embed any number of errors, and if you have a very bad failure, you're going to have everything printed out nicely. If you have tracing on, if you don't have tracing on, the print is still very nice, but it's not going to be able to point to the exact line that made your program fail. That's true for any asynchronous code. I have to say that our traces are compile time added, so they really have no performance penalty. There is a 1.5x. They are 50% slower than without traces. But if you consider that without traces, we are like 5 to 6 or 7 times faster than a native promise. I personally run these in production with tracing on. So whenever I get a crash for any reason in the world, I have precise lines of code. And I'm going to show these very, very quickly. It's the last example. But let's get To the next one, we are still on composition. We saw we were composing in this syntax. It's nice, it's functional. Not everybody likes it, and it has something explicit. The idea of chaining stuff. So you're gonna like this API if you're really a functional developer that like to combine things in this way. Many times you do want to write things more imperatively, and a beautiful thing of TypeScript, we were able to exploit the generators syntax. So we can have, if you ever seen like the async await syntax, we can write in the same style. This is a generator. So t.gen is a combinator, it's a constructor that takes a function generator with an adapter, because the effects per se are not iterables or are not iterators, but we can convert them back and forth. And this adapter also allow us to yield multiple things, not only effect. For example, to access a service, rather than saying t.access and blah, blah, and just yield the tag directly. So I'm passing the tag and I'm getting back the actual function. And I can directly use those. Yield star, it's a trick. In reality, this means yield of another generator. It's a weirdness in TypeScript for, well, it's the only way that the types are gonna align, cutting short. The beautiful things in, if you use async await, you have no types whatsoever on error, or, well, input, they don't even have an input. Here, even though you're using an imperative syntax, everything is gonna be traced properly in the type system. That is very helpful in many circumstances, and you can really yield in any single place. So you can transform your imperative code into a purely functional code just by rewriting this in this style. But ideally, this is purely imperative. I'm assigning A, I'm assigning B, and I'm saying the result is this. It doesn't have the classical catch that the async await has. The problem is, it's not that we cannot implement it, it's that it loses completely the type. So I'm not going to implement things that are type losing. And you can still use all the combinators inside of a yield. And in this case, it's precisely the same program as we saw before, but this time wrote in a completely imperative looking way. Let's get to the interesting part. We only spoke about effects. Take an input can fail. We said managed resources are important. Let's begin doing something managed. We're gonna quickly build. We're gonna use the PG Postgres library to access a PostgreSQL, and we're gonna run a very simple query. The console service, precisely the same as before. Here we wrote an utility to read something from the process.environment. So it's like the actual configuration. You might want to have a connection string in the environment or whatever. Same as before, make pg full config. This makes an effect. It makes, well, yes, it makes an effect. Same as before, we extract the tags. And we say that this is the configuration. Here, we're going to say a generic configuration. So this is overridable, and you can, in test, use a different one. Provide live, as we saw before. Here, first time, we hit a manage. the pool. The connection pool has to be open and has to be closed. Closing a connection pool is an effectful operation. Opening it, it's not. In this case, what do? We access the configuration. We create the service. We could have wrote this using the generator syntax. I'm just ping pong in a ping pong from one syntax to the other to get you familiar with both approaches. There's really no strict preferences. M is from the managed module that we saw before. And here we are saying make exit takes an effect as the open part and attach it to a finalizer. And in this case, in the finalizer, we close the connection pool, saying if this fails for any reason, we're gonna die. It's a defect of the code, so it doesn't appear in the error channel. It's not something predictable. And in any case, finalizer can only die because there is really no way that you can handle a finalizer error in a standard way. If a finalizer has failed, like a resource has not closed, it's something you probably want to crash. So even in Zio, that's the standard. You could widen the type, but then it kind of loses the semantic. The init part can fail for checked exceptions, and you can easily handle the opening error. Closing happens when your program ideally is done. So that's really another part. Anyway, this is a managed. So the managed has three parameters like effect. This managed to construct this managed, we need the pool config. It can never fail, and in case of success, it returns our PG pool. We build a tag. Before, providing is a little bit more tricky. We have to use this is a function that explicitly takes the effect. Actually, there is even a helper to do this, but I wanted to make it explicit. So you see what's going on behind the scene. You could say provide service manage, PG pool, and you have to say make PG pool. Is exactly the same data type as we see here, but it's written explicitly. We are providing by allocating the manage, taking the pool, and providing the pool to the effect that is passed in. To get a connection, another manage, connection is something live, has to be opened, has to be closed. So we take the pool and we say the connection is allocated through connect, and upon exit, it has to close, releasing back to the pool. As you see, the release is not effectful in this case, returns a void, because the connection is just pushed back in the connection pool. Same logic as before, we extract the type with the helper. Provider, same code as before, quite standard. Let's use it. In an effect, we access the connection from the environment. We use it normally, and you see that this is an effect that requires a PG connection. And let's use that in a program that also use the console service. And here, this is gonna query the database, and it's gonna, return a name. I'm not gonna do a full migration over the database. It's slightly out of purpose, but it is gonna connect to a real database in a matter of a few minutes. How do we run this? Same logic as before. We have to provide services one by one. Let's see. If we don't provide anything, that will have a compiler error saying first we don't have a console service. So let's provide the live console service. This time we require a PG connection. So we provide live PG connection. That needs a pool. Provide pool. That needs a config. And that's finally it. This no longer requires anything and can run. This is already potentially testable and anything else. But before getting to the test, I want to make the final step into the abstraction. As we said, this is a dependency tree. We're building dependency trees by passing stuff. So this is looping to a series of providers. It's not the most efficient way, and by all means, it's not even totally nice. It is sort of nice, but can be widely better. We get to the point of layers, precisely the same code as before. We import the layer data type, and we can say that the live console service, it's built from an effect, from this specific effect. And this is going to be a layer that doesn't need anything, cannot fail, and will provide to the program that consumes it a console service. Same code as before. PG pool, live PG pool, doesn't require anything, and get makes a PG pool config. The pool itself is a managed. Instead of saying from effect, we say build a layer from a managed. And this will be a layer that requires the full config to be provided. Here, we are packing them together. And this is a really nice thing, composing declarative layers. You have various operators. You have plus, 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 which means parallel. There is no interdependency between the two, so they can bootstrap in parallel. Clearly, that's not the case because the live PG pool requires a pool config. The direction of the arrows means what provides to what. If left is provided to right, or if right is provided to left. With a plus means not only provide it to the other, but also merge the output. So let's see the difference. Here we have a layer that doesn't require anything else and has a PG pool config and a PG pool. I could say this, and this is only providing the PG pool, so the pool config is internal. And if I use the plus, 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 this is still gonna require a PG pool config because they are constructed in parallel. So I'm not providing one to the other. This, as we see, is a very declarative way to compose multiple layers. Those things can be concatenated, and you can have hundreds of layers. The single layers are automatically memoized upon starting the program. So if you use the same layer in multiple parts of your application, of your dependency tree construction, you could imagine you might have multiple things that need the PG pool config. Well, in this case, not, but in general, you might have multiple places where you want to use the same layers while still embedding them inside other things. The layers will be automatically memoized and not reinitialized. If you want a fresh version of a layer, you can say l.fresh, and this is going to construct a fresh instance. So it's not going to be fetching from the cache. The memoization is done through, it does also synchronization. So if you have multiple asynchronous stuff, when one layer is constructed, if the same layer is required by another in another place, the other will wait automatically.
Can I just jump in quickly, Michael? Sorry, we're coming near to the end of our time, so I thought it would be good to give people a chance to ask any questions that they want to.
Yeah, I just have the final example because I want to show this tested. The test. It's only the test left. I have one file. So how do we test this? That was the final point. The program is the same as before. We use it. We provide a connection. In this case, this is a local connection. We taking a connection from the pool and using it is not really a global thing. So it shouldn't go in a layer. For that, we still use the same providing mechanism for the managers before. This is our final program. How do we test it? Test the whole test. We have a test PG pool config, and we use the live PG pool. We provide a test console service. This is a test runtime that allocates a layer, basically, upon spinning up the thing. Whenever I run the test, it's going to allocate this layer and use this layer in any of the tests below. So here I define something. So a basic test, it was a query, a dummy query. How this is built, very easily. You can take a look at the documentation of test containers, but ideally it's a managed that spins up a Docker container. It gets the mapped port, and it builds out a configuration from the newly created instance of a Postgres. So this doesn't require anything and provides the config. Test the test. Let me run the test. It's going to be the final thing. I want to show watch Docker. Yes. Run the test. Have the few tests before. Spinning up a container. Postgres is up and running. And the test passes. In 7 seconds, we have on demand a newly created instance of Postgres that doesn't conflict with anything else. And this is, in my personal opinion, a nice way to do integration testing, for example.
Yeah, I definitely agree. I've used test containers myself for other projects, and it's pretty handy to be able to just say, here's some blank scratch database, go nuts. Yeah, definitely. So yeah, that was really cool. Thanks, Michael, for that talk. That's it's really great of you to come and talk with us today.
Thanks to you guys.
Maybe let me highlight some of the comments from the chat. So Dara said, likes the distinction between defects and errors. Maybe you can briefly expand on that.
Sorry?
So Dara's asked about, you made a distinction between defects and errors. Is there anything you want to expand on that one?
I can, definitely. So let's take so this is a checked exception. And as you can see, we have it in the type. Having a checked exception in the type allows you to handle the exception in a decent way. Of course, the handler can again raise other errors and similar things. A non-checked exception is raised to a die. A die doesn't appear on the type. the program actually exits. We can access the full cause. If, for example, this program dies. You can say sandbox, and in the sandbox, effect type, you see that the error here is a full cause of an error. Cause itself let's take a look at what's inside a cause. Cause is a data type, is an IDT. It's a union, actually. Tagged union of a failure. Failure is a checked failure. Then represent a sequence of two errors. We have parallel combinators. We have sequential combinators. We have managed. We have, as we said, resources, layers. So when something fails, can fail for multiple reasons, then indicates two errors that have happened in a sequential order. Both means two errors have happened in parallel. Traced means we have an additional trace on the specific error. Empty, it's kind of the well, it's an empty cause. It's used for initial composition to have sort of like a monoid rather than cause itself is for the mathematics people, it's a free semi-ring. So it has where it's a semi-ring in the two operations then and both, where the empty is the identity element, die is for the die causes, for the defects, and interrupt is for interruption. Those are clearly, it's a recursive data type. Transverse these is not the easiest thing to do, but combinators like run main that we saw before, this one, here I've built an example of a very dumb computation, but that at the end fails. I'm not actually handling this error anywhere. So this is gonna fail brutally. And whenever this fails brutally, you're gonna see in the output, if you have the tracing setup, you're gonna see something like this. So it's gonna say a checked exception was not handled, gives you the check exception. It gives you the fiber continuation, so where it was supposed to go after it, and it failed before, and you have the full execution trace, so you can follow kind of line by line what the hell happened in your program.
Yeah, that's really cool. So I just want to highlight some of the other comments as well. So Alfred's asked, when should you prefer a service over a layer?
When should you prefer a service over a layer? When it's a local environment. Layers are for global dependencies. They are heavy to initialize. As I explained before, they are memoized. There's a lot of synchronization happening. So they are not the fastest thing. They have a overhead, which clearly is not relevant when you have to bootstrap dependencies, because you're going to bootstrap 100 dependencies and pay the overhead only at the beginning. But for example, here we had taking a connection from the pool. This is a thing that is going to happen, for example, if you have an HTTP server, this is going to happen at request time. You don't want to initialize layers at request time. That's an overhead you don't want to pay. In this case, local, you do want to use a service. So a local environment.
Cool.
Was it
Thanks
clear?
for that. Yeah. And one from my co-organizer James, who says, have you ever tried using this in a front-end context, like maybe inside React or something like that?
Yes, there is an example even in the GitHub of the organization where we use it in React. There is a catch. Effect is asynchronous. React is synchronous. So if you use stuff like Next.js, it's not totally nice to, well, use it for, I personally use it for structuring the dependencies. So instead of using the React context, I want to use this stuff, but I use the synchronous data type, which is not effect to do that part. There is another data type, which is called sync, which is not built on effect. It has exactly the same type parameters, and it has a very similar API, but this time it's synchronous. So these types of computations will run synchronously, and for that, it's really nice to use in React. Another really good example of usage in React is for the stream data type, where I have one contributor of effect.ts that is basically using Redux epics. Instead of using the observables, you're using streams. Again, streams have a very similar API. They're pool-based streams. They have the 3 parameters and access the environment. It's going to be very similar to effect, but it's actually doing a stream of computations. So this is very nice for doing effectful things like like you would do with observables in the context of a Redux observables or similar. In general, I have to say there is a price we paid when we use effect in the front end. Minimum bundle size is going to be about 50 to 70K. It's not the tiniest thing. So if you use it intensively, it's totally fine because you're going to amortize it. You're going to amortize very quickly. If you don't use it a lot, I would rather advise using the sync data type, which is very small, and the async data type, which is also very small. They work all in the same way, but async is not fiber-based. It's based on promises. So the code per se is more compact, and it's not going to use all the bundle size. Many times I find the complete effect system to be slightly overkill in the front end. But if you do use it a lot, then it's perfect and cost is completely amortized. It depends on the use case, but definitely.
Yeah, that's cool. Thanks very much for that. Any other questions for anybody? Get them in now. Otherwise, I think we might just call it there. But that was a really good talk. Thanks very much for coming on to speak. Really appreciate it.
Thank you for having me. It's really been a pleasure to be here.
Not at all. So I'll just put up a final announcement briefly. So if all of you on the YouTube stream, please feel free to join our Discord.
Please do, because I'm going to share the repository on that.
There you go. There's the hook. You can get the code from Michael's store. So that link should work, or you can scan the QR code, hopefully. I don't know how that works. I've not done it myself, but I'm going to take James' word for it. Basically, yeah. So, and if anybody on the talk would like to speak, just please get in touch, either on Discord, all of the organizers are there, or you can send us an email to lambdaloungemcr@gmail.com as well, if you want to get in touch. But yeah, that's it for January's talk. So thanks very much, and see you in February's talk, when it will be, I think it might be my co-organizer Sam talking about a Lisp parser that he wrote in Elixir, but watch the space. We'll find out. So thanks all, and good night.
Thank you, guys. Good night for